Dr. Mykhailo? Yes. So I call Dr. Mykhailo. He's going to talk about features of opal-based nanocomposite fabrication. Sorry for the delay.
Dear Chairman, dear colleagues, firstly, let me express my thanks to organizers of this conference to be in this suitable, very nice place. And now let me present the summary. I hope the intermediate summary of investigation initiated by Professor Mykhailo in Alexandria National University for about 10 years ago, and devoted to synthesis of opals and creation of nanostructures on their base. Brief review will be devoted to short description of problems which will be discussed. Then we consider some methods owing to we can obtain all dielectrical nanocomposites on the base of synthetic opal, and also metal dielectrics nanocomposite, and conclusion, of course. Synthetic opal are considered as very prospective materials for creating photonic crystals, for creating nanocomposites, owing to their regular 3D structure. And in our case, synthetic opals were prepared by sedimentation of silica dioxide spheres. Globals or spheres were prepared by standard Stiobe methods, and then after sedimentation under gravity forces, we obtained such a regular structure which form face-centered cubic lattice. The second step is the penetration of substances, or bedding of substances into opal pores. Synthetic opal are porous structure. They belong to colloidal crystals, or so-called self-assembled structures, and their pores can be filled with any substances in many various ways. Well, if you do it, we have regular structure with active components, and if you want, you can chemically remove silica dioxide globals and obtain inverse opal structures. This structure can be used in many branches: optics and optoelectronics, energy storage system, communications, sensors, and they have biological applications. I would like to pay your attention to reviews by Lytle or Armstrong. Main questions I would like to answer in this report, and what impregation techniques should be preferable. There are four standard methods to fill opal pores. Solution-based technique, melt-based technique, chemical radiation-based technique, and electrodeposition. Electrodeposition is used for obtaining metal dielectric nanostructures, and all previous others are used for obtaining all dielectrical structures. It's very important to know with what filling degree we have your nanostructure and what state of substance inside of our pore. First, solution-based technique. We prepared nanostructures with KDP or lithium iodate, but now I would like to consider KDP. The first way is a typical way and so-called equilibrium crystallization, when your solution, water solution in this case, soak the sample, the opal, and then solution is evaporated at room temperature for several days. The first impregnation cycle, we have filling degree at about less than 10%, where C is concentration or solubility of KDP. And after next cycle, you have to increase the filling degree. But I have to say that there is a finish in such process, and it's due to the existence of a channel in our structure. Channel, and the characteristic sizes of globules is in our experiments is 300 nanometers, and the linear sizes of channels of pores is no more than 100 nanometers. And when you crystallize some substance in opal pores, the crystallization in pores may stop the penetration of the solvent inside opal pores in further cycles. After several cycles, the interference non-transmission minima in transmitting spectra of such structures is redshifted, and the filling degree is defined of this shift very well, and it's correlated with calculated. And the second way of solid-phase technique is so-called non-equilibrium crystallization, when we have solution at high temperature, at 50 degrees centigrade temperature, and so with this solution sample which are at room temperature. And non-equilibrium crystallization we have in this case because of rapid cooling of solution. In this case, the filling degree is higher, but in this case, KDP crystals grown inside opal pores, not classical KDP, and as you can see from X-ray diffraction pattern, there are differences, there are more differences, and it testifies that another phase of KDP is formed under using such method. Melt-based technique is more complicated. It's needed high temperatures, and in this case we put polycrystalline powder of substance we want to embed on the surface of your opal, opal, and then heat the whole system up to temperature slightly higher than melting temperature. And the solution can penetrate into opal pores, and then we cool our system and crystallization starts. And you can see from this table all substances we put in by using such technique and their melting temperature. According to literature data, opal matrix is stable up to 950 degrees centigrade. It's a very important remark, and it gave us the hope that no chemical interaction between opal matrix and the melt of substance. But characterization of such structures were performed by many techniques: scanning electron microscopy, XRD analysis, micro visible spectroscopy. We used visible spectroscopy to determine the film grade by shifting the Bragg reflection band. Well, and in the case of melt-based technique, the filling degree is up to 60%, 60% or more percent, in contrast to previous technique, solution-based, when for the first cycle of integration we have only less than 10%. Well, this micrographs. This is the surface of the obtained nanocomposite. This is some of the Raman spectra and some of the X-ray diffraction pattern. And in each case we have some features and some extraordinary results. For example, opal paratelluride, we have another phase under crystallization. You see, crystallization in our case is under other conditions than the usual. First of all, this is a restricted volume. Maybe another pressure inside opal pores. And the third, in our case, the surface played a more important role under crystallization. In case of opal lithium tetraborate, for example, we obtained alpha quartz phase control. And as our results testified, chemical, unfortunately, maybe unfortunately, chemical interaction between substance we embed and opal matrix exist. And features in summary of using melt-based techniques. And when we have temperature less than 850 degrees centigrade, or maybe 880 degrees centigrade, we have no chemical interaction with opal matrix. And in this case, we have the same substances we embed. And opal has amorphous state. This is a result of investigation of Raman spectra and X-ray diffraction pattern. Well, when we have higher temperature, we have obvious changing of lattice parameters of the embedded substance. And we have some crystallization process of silica dioxide matrix. In case of bismuth silicate, we have formation of two components, and at higher temperature we have transformation connected with formation of alpha quartz with maybe small traces of lithium tetraborate, but we are not sure for the existence of lithium tetraborate. So the evidence of the existence of formation of silicon dioxide on crystalline form is the Raman spectra, for example, Raman spectra of opal BTO, where in the high frequency Raman region we have narrow bands, and the second order Raman bands, which can be assigned to stretching vibrations of silica oxide for group. Well, and metal dielectric structures. We used electrochemical deposition under action of electrical force. Copper and silver ions penetrate into opal pores, and we reached the filling degree up to 10% for one cycle, but it depends on time duration and current value of electrochemical deposition. We prepared this structure in order to use them in future as surfactive structures, and previous results of our investigation is enhancement of photoluminescence of rhodamine 6G in the such metallodielectric structures. We have enhancement up to 4 times. Well, conclusions, the filling degree for one cycle is higher using opal-based technique, but the lack of this technique is that you can use this technique for one cycle. I'm not sure that after the second cycle of using male-based technique, we will have the same substance. Well, and the main factors that affect structure and chemical composition, restricted volumes, as I said, and chemical interaction between opal matrix. And I would like to thank our colleagues this work was performed with cooperation with Rudolf Holze, Bilal Bussal from Jordan, Rudolf Holze from Germany, Raul David Rodriguez from Germany, and Alexander Kolmes from Ukraine, Institute of Semiconductor Physics of National Academy of Science Ukraine. Thank you for attention. What particles?
How do you fix on the electrode?
Fix the electrode.
Yeah. How do you fix the particles of opal on the electrode? Not the
This. I see. These particles.
Yeah.
Oh. I understand. Just this. This globular and their range in bulk sample. It's a microscopic scheme. See, it's very scheme. Our sample was a plate with thickness of 2 millimeters, with surface area of about 2 centimeters of to the second power, and this is the globular, and our sample consisted of this globular. It's schematical image, no more. Yeah, we have plate and put it on the electrode. You see, it's only schematic, no more. We heated our sample with polycrystalline powder. We heated up to higher than melting temperature, and then we have liquid penetrated under capillary forces into opal pores. We keep this system for several minutes, and then we cool this system, and crystallization starts.
I'm wondering if you have measured electrical properties of your opals, like conductivity and so on.
We measured electrical properties for nanocomposite, just a moment, opal BCO, but its previous results, I reported them on conference on NANO2017 this year, and this structure have as dielectric, of course. We have activation energy. We propose electron conductivity, but we are not sure by now. Well, and we have an activation energy of about 1 electron volt, and the dielectric properties at 1 kilohertz of this composite was equal to 2. We have multi-phase system, and I have not said that an air may be in our composite inside volume of our cell.